we have looked at the proof of the sufficient part of the Kraft inequality. Now, we look at the proof for the necessary part of the Kraft inequality. So, the necessary part of the Kraft inequality says is that if the code is instantaneous, then it implies that summation of r minus Li from I is equal to 1 to q is necessarily less than or equal to 1. Let us try to prove this relationship. So, the proof goes as follows. Let us assume that the number of code words of length 1 is n1. So, because the code is instantaneous, it implies that n1 should be less than or equal to r, where r is the size of the code alphabet. Now, because the code is instantaneous, the code words being used may not form the beginning of another code word. Thus, we have r minus n1 first code symbols remaining. So, once I have chosen n1 code words of length 1, the remaining are r minus n1, which can be used as a prefix for the code words. So, similarly, for the number of code words of length 2, we have n2 should be less than or equal to r minus n1 multiplied by r. R minus n1 are the prefixes left out. This gets multiplied by the size of the code alphabet, which is r. So, this is the number of code words which I can form of length 2. Now, since the code is instantaneous, if I assume that, then the number of code words which I have of length L2 of length 2, that is n2, should be less than this quantity, and if you simplify this quantity, it turns out to be this. Similarly, I can show that code words of length 3, that is n3, should be less than or equal to this expression on the right hand side here. This again is the number of prefixes of length 2 which are left out, that gets multiplied by the size of the code alphabet, and this total number gives me the number of code words of length 3 which I can form. And since the code is instantaneous, the actual number of the code words of length 3 which we have, that is we call n3, should be less than this. Now, if we assume that L is the maximum length of the code words, then and NL is the number of code words which we have of this maximum length L, based on this derivation which we had done earlier, we can show that NL is less than this expression on the right hand side here. Now, if you take this expression and divide by RL, we get expression is this. After taking this quantity, after dividing by RL on the right hand side, we get this quantity. This quantity we can write as summation nj r minus j less than or equal to, where nj denotes the number of code words of length j, and j can range from 1 to the maximum length which we have in the code, and that is L. Now, if you write this out, we will get 1 by r plus 1 by r. The number of terms corresponding to 1 by r will be n1, number of terms corresponding to 1 by r2 will be n2, because this corresponds to a code word of length 2 and this corresponds to a code word of length 1, and similarly this corresponds to number of code words of length r L. So, this expression is equivalent to this expression which I have. Now, summation of n1 plus n2 plus nl should be equal to q, that is the size of the source alphabet which we have. So, n1 plus n2 plus nl is equal to q, that is the total number of code words. So, that this inequality which I have written here is identical to writing r minus li less than or equal to 1. So, this is a proof for the necessity part of the Kraft's inequality. Now, we have seen that instantaneous code is a subclass of a uniquely decodable code. What this implies that the sufficient part of the Kraft inequality should be also applicable to the uniquely decodable code. What I mean by that is that if this quantity is satisfied, then I should be able to synthesize a uniquely decodable code. Now, the next question is that is there some restrictions on the length if the code is uniquely decodable, and we will find that the necessity part of the Kraft inequality also applies to uniquely decodable code. So, what I mean by that is that if the code is uniquely decodable, then like in the case of instantaneous code, this inequality has to be satisfied. Correct? So, let us try to prove this inequality for uniquely decodable code. Now, this inequality which says that if a code is uniquely decodable, then this is satisfied, was first discovered by Macmillan. So, what we are going to discuss is Macmillan's inequality. So, if we assume that a code is uniquely decodable, then what I have to prove is this is true. Okay. So, the proof follows as follows. Let me consider a quantity raised to n. Now, this is equivalent to writing r minus when I expand this equation, then we will have qn terms, each of the forms r minus li1 minus li2 minus. So, when I expand this, I will have q raised to n terms, and each term will be of the form given here. This will be equal to r raised to, let me call it r raised to minus k, where by definition li1 plus li2 plus lin is equal to k. Now, let me assume that L is the maximum length of the code word in that uniquely decodable code. Right? Now, K can assume some set of values from n to nl, and let us define nk as the number of terms of the form r raised to minus k in this equation one. Then I can write this expression as this expression can be written as summation of nk r raised to minus k, k is equal to n to n l. Now, if you look at the expression equation number 3, we see that nk is also the number of strings of n code words that can be formed, so that each string has a length of exactly k code symbols. Now, if the code is uniquely decodable, then this nk must be no greater than r raised to k. So, if the code is uniquely decodable, nk has to be less than or equal to rk. This r raised to k is the number of distinct r array, this is distinct r array sequences of length k. So, this is the number of distinct r array sequence of length k, and since our code is uniquely decodable, nk has to be less than this quantity. What it implies that r minus li n I is equal to 1 to q should be less than or equal to r raised to k, r raised to minus k, k is equal to n to nl, and this simplifies to nl minus n plus, in fact this is equal, and this is less than or equal to nl. Equation 5 is the proof we seek. Now, if k is greater than 1, then x raised to n will be always greater than nl if we take n large enough. Now, in our case equation 5 holds for any integer n. So, what it implies that x should be less than 1, and in our case x is nothing but this quantity out here. So, this implies that r minus li I is equal to 1 to q should be less than or equal to 1. So, if the code is uniquely decodable, we have proved that this condition has to be satisfied. So, this condition is valid both for uniquely decodable code and instantaneous code. So, sometimes the Kraft inequality is also stated as Macmillan-Kraft inequality, because it is true for both instantaneous code and uniquely decodable code. Now, before we go ahead, let us look at a couple of examples to understand the proof which we have provided in the Kraft and Macmillan's inequality. So, let us assume that I have a source consisting of 10 source symbols, and let us assume that this source symbols have to be coded using a code alphabet which is trinary in nature. So, it has got 3 symbols 0, 1, 2. I want to code this source into a trinary instantaneous code, and I have been also given the code word lengths for this source symbol. So, let me assume that the code word lengths corresponding to this 10 source symbols are 1, 2, 2, now, if we want this set of code word lengths and want to design an instantaneous code, the first thing we have to do is basically check whether it satisfies the Kraft inequality. So, to check that, let us do it. Since we have 10 source symbols, this turns out to be equal to 1/3 plus 5 1 by 9 plus 4 1 by 27, and this is equal to 28 by 27, and this turns out to be greater than 1. So, what it means that I cannot design an instantaneous code for this source with this code alphabet where the code word lengths are given by this set. It is not possible. So, let us take another example. Suppose there was a source S consisting of 9 source symbols, and again my code alphabet consists of 3 symbols 0, 1, 2, and I want to design an instantaneous code with the code word lengths given as now. Before we start designing of an instantaneous code, it is essential to check whether this set of the code word lengths satisfies the Kraft inequality. So, let us do that, and if you substitute the values into this expression, we get this to be equal to 1. So, what it implies that it is possible for me to design a instantaneous code with this set of code word lengths. So, let us do that. So, I can take the first symbol S1, I will assign 0, to S2 I will assign 1 0, S3 I will assign 1 1, S4 I assign 1 2, S5 is 2 0, S6 is 2 1, S7 is 220, S8 is 221 and S9 is 222. Now, note how the construction of this code illustrates the coding method used in the proof of the Kraft inequality. We use one prefix of length 1, namely 0, for the source symbol S1. This left us with two prefixes of length 1 for the other code words. Now, what it means that we will have 2 times 3, that is 6 permissible code words of length 2. Out of this, we have used 5 for the source symbol from S2 to S6. So, this leaves us with unused prefix 22 for the remaining code words. So, with this prefix which is left out and the code size to be 3, we have 3 more code words of code word length 3, and now exactly we have 3 source symbols left out. So, we can assign the remaining code words of length 3 to the remaining source symbol S7, S8 and S9. So, this helps us to understand the coding method used in the proof of the Kraft inequality. Now, we have seen how to construct instantaneous code which map source symbols from a source alphabet to code words consisting of code symbols from code alphabet. Now, for a given source S and for a given code alphabet X, we can form many instantaneous codes, or for that matter many uniquely decodable codes. Now, with so many abundance of available instantaneous and uniquely decodable code, the natural question is, how do you select the best code from this lot? Now, to do that, perhaps you have to use some kind of a criterion, and the natural criterion for the selection, although by no means the only possibility, is length. So, we can look at the length of the code words of a code to select a particular code. Now, if there are no other considerations from the standpoint of mere economy of expression and the resulting economy of communication system, we prefer a code with many short code words to the one with long code words. What it means that we should define what is the length of a code. Now, a code consists of code word, and since each code word could be of different length, we have to define what is known as an average length of a code. So, let us define an average length of a code. Let a block code transform the source symbols S1, S2 up to SQ into the code words x1, x2 up to x cube. Let the probabilities of the source symbol be P1, P2 up to PQ, and let the lengths of the code words be L1, L2 up to LQ. Then we define the average length, which is denoted by L. This is the average length of the code by the equation by definition. Now, we will not write here average. It is understood that whenever I write L here, it means the average length. So now what the problem reduces is that we should look at only those codes for which the average length of the code is as low as possible. Now, this leads us to another definition of what is known as a compact code. So, let us define a compact code. Consider a uniquely decodable code which maps the symbols from a source S into code words composed of symbols from an R-array code alphabet X. Now, this uniquely decodable code will be called compact. The definition of the compactness is associated with the source S. So, this code will be called compact for the source S if its average length, which is denoted by L, is less than or equal to the average length of all other uniquely decodable codes for the same source and for the same code alphabet. This is a definition of compactness of a code. So, now the fundamental problem of coding information sources is finding compact codes. Now, what we will do basically, we will restrict our search for compact codes to the class of instantaneous code, which is a subclass of a uniquely decodable codes. The reason for doing this is that Macmillan's inequality assures us that any set of code word lengths available in a uniquely decodable code is also available in an instantaneous code. Because of this inequality, we can look ahead for synthesizing of compact instantaneous code. Now, this definition of average length is also valid for both zero memory source and sources with memory, including Markov sources. But for our discussion at the moment, we will restrict ourselves to zero memory source. Now, the question that comes to our mind is there any kind of relationship between the information measure and this average length? In order to answer this question, let us examine little more in depth. So, let me assume that I have a source S with source symbols given as S1, S2 up to SQ, and this is the block code with a code alphabet X1, X2 up to XR. So, we have R array code alphabet, and for time being let us assume that this source is a zero memory source. With this source symbols are associated the probabilities P1, P2 up to PQ, and with each of these source symbols are associated the code words composed of code symbols from this code alphabet X. So, associated with this code words, we have the lengths for this code words as L1, L2 up to LQ. Now, for this zero memory source, we know that entropy of the source is given by now let Q1, Q2 up to QQ be any Q numbers such that each Qi is greater than or equal to 0 for all I, and we also assume that the summation of Qi is equal to 1. Now, we have earlier in this course seen an inequality which says that summation of xi log of yi xi I is equal to 1 to q is always less than or equal to 0, provided xi greater than 0, yi is greater than 0, and summation over xi and summation over yi is equal to 1. So, if these conditions are satisfied, then this is a valid inequality. Now, considering Pi and Qi in place of xi and yi respectively, we can write summation of Pi log of Qi Pi is less than or equal to 0, which implies that summation of Pi log 1 by Pi I is equal to 1 to q is less than or equal to summation of Pi log of 1 by Qi I is equal to 1 to q. Now, this will be equality. So, with equality, if and only if Pi is equal to Qi for all I. Now, this expression out here is your Hs. So, on the left hand side I can write as Hs is less than or equal to summation of Pi log of Qi. So, this becomes negative. So, with equality, if and only if Pi is equal to Qi for all I, this condition is with equality. Now, equation 1 is valid for any set of non-negative numbers Qi which sum to 1. We may therefore choose Qi to be r minus Li over r minus Lj, j is equal to 1 to q. If we choose our non-negative Qi as given by this expression, then we can write Hs, this equation number 1, as less than or equal to minus summation of Pi log of r plus Pi log of substituting this into this, we get this expression, and this expression on simplification will result into the following expression. Plus log of summation because summation of pi I equal to 1 to q is equal to 1. Therefore, this expression reduced to this expression, and this by definition of the average length is L log r plus log of now. If we have the requirement that our code is instantaneous, then the Kraft inequality tells us that this quantity out here should be less than or equal to 1. Now, if this quantity is less than or equal to 1, then the logarithm of the quantity less than or equal to 1 will be always less than or equal to 0, and in that case we can write this as Hs is less than or equal to L log r. So, we can say is 2 and this is expression 3a. So, or Hs by log r is less than or equal to L. Hs is measured in bits, L is the average number of R array symbols we use to encode S. Now, if we measure the entropy in R array units, then equation 3 can be written as HRS, this equation out here. When I write Hs in terms of R array units less than or equal to now, it should be noted that equation 3 constitutes a milestone in our study of information theory. This equation is the first instant which demonstrates the connection between our definition for information measure and a quantity, in this case L, which does not depend upon that definition. So, this equation provides some kind of a justification for the definition of our information measure which we had started earlier in the course. Now, on the surface equation 3 merely presents us with a bound on the average length of a code. So, what it says that the average length of an instantaneous code which is given by L has to be always greater than or equal to the entropy of the source measured in R array units. Now, in certain cases, however, it is possible to show much more from the simple arguments leading to this equation. So, let us carefully examine the conditions for equality in this expression out here which we have derived. Now, the inequality was introduced at 2 points. First, at this point, that is equation number 1, and the other was at this point. So, if we assume that the code is instantaneous, then, and we assume one more thing, that summation j equal to 1 q r minus Lj is equal to 1, then this will be an equality. So, this will not be dropped out from this expression. So, in this equation, a necessary condition for the equality rather than the inequality is this term out here should be equal to 1. And then retracing our steps to this equation, we see that a necessary and sufficient condition for equality is Pi should be equal to Qi for all I. What this implies that equal to Q, and this is equal to 1. So, if I have Pi satisfying this relationship for all I, then I will get the equality, that is HRS is equal to L. So, this also means that log of R 1 by Pi is equal to Li for all I. Now, so summarizing, for an instantaneous code and a zero memory source, we will always have L greater than or equal to HRS. Furthermore, L can achieve this lower bound of HRS if and only if the code word length Li equal to log to the base R of 1 by Pi for all I. So, it means that if this condition is satisfied for all I, then I will achieve the minimum length, and that minimum length is the entropy of the source measured in R array unit. Now, this condition is equivalent to saying that Pi must be of the form 1 by R alpha I, where alpha I is positive integer. So, now with this result, we have derived an additional condition for the word length of a compact code. What it says that if Pi is of this form, then where alpha i's are the integers, then not only will this be satisfied, but we have also derived the code word length Li of a compact code, and Li is nothing but equal to alpha I. And having obtained the code word length, the construction of a compact code follows the procedure of the example discussed earlier in today's class, when we design a code for a source consisting of 9 symbols and a code alphabet consisting of trinary symbols. Now, let us try to answer some of the coding questions raised earlier in the light of what we have studied today, an important relationship which says that L should be always greater than equal to HRS. So, in the light of what we have derived today, let us answer some of the coding questions which we had raised earlier, and we will try to do this with the aid of some examples. And this we will have a look at it in the next class.